Welcome back. We were discussing the single phase induction motors, and in this particular lecture we are going to take our discussion forward with the types of single phase induction motors. A single phase induction motor is inherently not self-starting. So this we were discussing for the past 3 lectures, that the single phase induction motor will not be self-started, and if some auxiliary winding is added here, then it can be made self-starting. So to make the induction motor self-starting, some methods can be employed to produce a revolving magnetic field. So earlier the magnetic field was pulsating in nature because you have the backward field and the forward field, which cancel out each other as it create the pulsating magnetic field. So the pulsating magnetic field has to be converted to revolving magnetic field using some starting methods which are used for making the motor self-starting. So this can be achieved by converting a single phase supply to two-phase supply. So we have seen in the previous lecture also that the single phase induction motors are basically temporarily we run that as two-phase motors. So we have to convert the single phase supply into two-phase supply, and we will be using an additional winding which may or may not be disconnected once the motor starts and pick up the speed. So these additional winding may be removed from the network when the motor starts, or it can be present in the network as it is. Or we can create another field by induction process using a short circuit band or a ring. So we can also use two external methods to produce some field which will help the main field to create the revolving magnetic field. So depending on the method used, single phase induction motors can be classified as, the first classification is split phase motors, which are started by employing two-phase motor action through the use of an auxiliary winding called starting winding. So we use starting winding, which are one of the categories of single phase induction motor known as split phase motor. Second, we have the capacitor motors. So capacitor motors started by employing two-phase motor action through the use of auxiliary winding with a capacitor. So we have a capacitor present in the auxiliary winding. So that is why the name has been given capacitor motors. The third type of motor is basically the shaded pole motors, which are started by the interaction of the field produced by the shading band or short circuiting ring placed around the portion of the pole structure. So these bands or rings are basically used to produce the external magnetic field by the induction principle. So that is known as the shaded pole motors. Now we will see the first classification, which is split phase machine. So in the split phase machine, the circuit diagram is given and here the phasor diagram is given. We will be having one main winding. So this is the main winding which is present in the stator, and the rotor is screw cage induction motor, and this main winding is responsible for continuous operation during normal running condition. So during normal running condition, the main winding will be functioning and it will be connected directly to the power supply. So here we have the single phase supply which is connected to the main winding with relatively large number of turns of wire. So here if you see, the number of turns of the wire will be more. There will be a starting winding. This is the starting winding, which is another set of coils around with fewer number of turns. So the number of turns here will be less as compared to the main winding, and these are electrically displaced from the main winding to create a phase difference of starting torque. So the main winding and starting winding will have electrical phase difference. So here the phase difference is basically, ideally we have 90 degree to create the starting torque. Now there is a starting mechanism. During the startup, both the windings are energized. So from the supply, single phase supply, the windings will be energized, and the phase difference between the current in the main winding and the starting winding creates a rotating magnetic field. So rotating magnetic field is produced in the single phase induction motor, which was earlier pulsating, and it provides a starting torque. There is some centrifugal switch which we have seen in the diagram. This is the centrifugal switch which is connected with the starting winding. So the centrifugal switch prevents continuous current drawn by the starting winding during normal operation. So the current which is drawn by the starting winding, it will prevent during normal operation. Normal operation means when the motor has started and it is running at constant load. So it is activated by the centrifugal force at a certain speed, around 70 to 80% of the full speed. So when the motor gather a speed of 70 to 80%, it is activated and it is disconnected from the starting winding from the power supply. So this is your auxiliary winding and you have a centrifugal switch. So if the switch opens, no current will be flowing here. All the current will be flowing through the main winding and the main winding will be in function. So during the running state, after disconnection, the motor continues on single phase power using only the main winding. So only the main winding is present and it is the single phase power. So earlier it was two phase motor, temporarily it has been converted. Now the main winding optimized for efficient operation under normal running condition. So the optimization of the main winding is done under normal operating condition. Optimization means in terms of the current and in terms of the load, how much load we have to put in the single phase induction motor. So application wise, if we see, it is commonly used in applications which require moderate starting torque. So if the torque is moderate, like fans, blowers, small tools, there we prefer these motors, and it is a cost effective solution for single phase lighter starting loads. So when the load is lighter, then we prefer split phase and it is a cost effective solution. So here we can see the torque speed characteristic of the split phase single phase induction motor. You will be seeing that during the starting operation, the torque will be around 200% of the full load torque, and then under running condition it will be running under the constant torque operation. There will be a centrifugal switch which will be coming in operation here when the motor speed is around 70 to 80% of the full load speed. The next category of motor is basically the capacitor motors. It is also called split phase motor, where a capacitor is connected in series. So the capacitor will be connected in series with the starting winding. Earlier we were having a centrifugal switch which replaced with the capacitor. The design represents an improved form of the traditional split phase motor. So split phase motor design is improved to we get the capacitor motors. And the angular displacement between the starting current and the main current can be made nearly 90 degrees. So we have the current which is angle between the starting current and the main current. It is close to 90 degrees. Hence, we get high starting torque which are obtained because the starting torque is directly proportional to sine of angle theta. We know that the starting torque will be proportional to sine of theta, where theta is basically the phase difference between the starting current and the main current. So this is close to 90 degree, hence we get high starting torque. The capacitor in the starting winding may be connected permanently or temporarily. So this capacitor, either it will be connected permanently or temporarily. Then the capacitor motors are again classified into depending upon what type of operation it has. So the first classification is the capacitor-start motor. Capacitor in the starting winding is used to provide a phase shift during startup or high starting torque. So this is the function of the capacitor which will be giving a high starting torque, and hence it is known as capacitor-start motor because it will be starting the motor. Now second classification difference is basically capacitor-run motor, where the capacitor in the starting winding remains connected during the operation. It is not disconnected and it improves the efficiency and the performance. So efficiency will be improved and performance will be improved. The third category where you have the capacitor start and capacitor run motor. So combination of these two, whatever we have discussed in the first and the second point. So it combines the features of both the capacitor start and capacitor run motor for optimized starting torque and continuous operation efficiency. So starting torque will be high and efficiency will also be improved. So these are the broad three classification of capacitor motors. So if you see the first classification where you have the capacitor start motors. So capacitor start induction motor, basically it is called. Here you have a capacitor which is of large value to ensure high starting torque. So if you see here, the capacitor is connected in series with the starting winding and centrifugal switch is also there, because this capacitor has to be disconnected from the circuit in normal operation. And the starting torque of sine phi will be there, where phi is basically the phase angle between the main current and the starting current, and it will be significantly achieve a high starting torque. So high starting torque will be achieved. The capacitor employed is of short time duty rating. So this capacitor is basically generally present for short time. The capacitor is used is of electrolytic type. So electrolytic type capacitor is used, and this electrolytic capacitor is connected in series with the starting winding. As I said you here, the capacitor and the winding are in series, and the centrifugal switch will open after certain time, which is of short time, and then the capacitor will be disconnected. So the name start is being used. So when the motor attains a speed of about 75% of the synchronous speed, the starting winding is cut off. So we don't have the starting winding present, and the capacitor connected with the starting winding also get disconnected. The construction of the motor and the winding is similar to usual split phase motor. So how the split phase motor is there, the construction remains the same, and it is used in application where high starting torque is required, such as refrigerators. So generally in refrigerator we prefer capacitor start motors. And the speed of the capacitor start induction motor is almost constant within 5% slip. So within 5% slip variation will be there, and the speed will be mostly constant as the user required the demand. So the type of motor develops high starting torque, approximately 4 to 5 times the full load torque. So here you will have 4 to 5 times the full load torque that you will get at the starting position. And it draws a very low starting current, which is beneficial for efficient operation. So the current drawn is also very low. We don't require very high current. Direction of rotation can be changed by interchanging the connection of either the starting or the running winding. So if you change the connection of the starting or the running winding, you will give a different direction of rotation of the motor. So here you can see that the starting torque is about 4 to 5 times of the full load torque, and under the running condition, here the centrifugal switch will be opening and you will get a constant torque operation at a slip of around 5% variation here. The third classification that we have is basically the capacitor-run motors, which are also called fan motors. So it is under the running condition, it will be present, and here you have a paper capacitor which is permanently connected. So capacitor is permanently connected in the starting winding. So you can see a capacitor which is connected permanently, it's not disconnected. So you don't have any centrifugal switch connected. So an electrolytic capacitor cannot be used because it is designed only for a short time. So we have seen that the electrolytic capacitor is basically used for a short time. So electrolytic capacitor we don't use, we prefer paper capacitor here. And it cannot be permanently connected in the winding, the electrolytic capacitor. So paper capacitor is the one which is preferable here. So in this case, both the main and the starting winding are of equal rating. So the main winding and starting winding are of equal rating, so that whatever the current is coming here, the current can be equally distributed. And the performance and characteristic, if we talk, then the starting torque is lower here. If you see the starting torque, it is quite lower, which is 50% to 100% of the full load torque. In previous cases, we have seen it is 4 to 5 times or 400%, we can say. So here you will be having less, and the power factor is improved, possibly approaching unity. The better power factor will get efficiency. If we compare, then it is improved to have about 75% efficiency you can get. And the applications are basically used in fans, room coolers, portable tools, and other domestic and commercial electrical applications. So these are the application of capacitor run motors. Now the last classification, where you have a capacitor start and capacitor run. So you have a centrifugal switch also, which will disconnect, and you will have the permanent capacitor also. So here two capacitors are used, one for starting purpose and other for running purpose. So centrifugal switch will open the capacitor start motor, and the paper capacitor will be present in the capacitor run motors. So for starting purpose, you will have electrolytic capacitor as discussed, which is disconnected from the supply when the motor attains 75% of the synchronous speed, and it is adjusted by centrifugal switch. So here if you see, the centrifugal switch is there. This is the electrolytic capacitor, which will be opening after the motor attains 75% of the speed. But the paper capacitor will be in operation continuously, and it will be remaining in the circuit with the connection with the starting winding under running condition. So if you see, the starting torque has improved now. The starting torque is around 3 times of the full load torque. So the CS value is of higher value than of CR. So if you compare the paper capacitor with electrolytic capacitor, the electrolytic capacitor is of higher value compared to the paper capacitor. And the performance and characteristic, if we talk, it operates as a two-phase motors, providing the best performance and noiseless operation because you have both capacitor start and capacitor run. Torque is high and you have a low starting current. It provides a better efficiency and a higher power factor. The only disadvantage is that the cost will increase because you have two important capacitors connected in the network. The last classification, which are for the different ways of production of the field, is basically the shaded pole induction motor, which is constructed with salient poles in the stator, and each pole has its own exciting winding. So this exciting winding is produce its own field. So here if we see, this is our stator, which we have the rotor, and there is a squirrel cage rotor here present. These are basically the poles which are connected in the network, and you have the single phase supply given, and 1/3 portion of each pole core is surrounded by a copper strip forming a closed loop called the shading band. So here if you see closely, then you will find some bands are present in the pole core and in the stator core. So these are basically the poles where the field is produced, and this shading band is the one which is production of the field, responsible for the production of the field. And the rotor is usually of the squirrel cage type. So the rotor is no changes is there. The rotor whatever is present here, that will be squirrel cage type. And when a single phase supply is given to the stator, which is the exciting winding, it produces an alternating flux. So here you are providing a single phase supply and you will get some flux produced. So due to the presence of the shading portion or shading band, external field will be produced. So when the flux is increasing in the pole, a portion of the flux attempt to pass through the shading portion of the pole, inducing an EMF and current in the shading band or copper ring. So the flux is again produced by the single phase supply, and it will induce an EMF and the current in the shading band. And as per the Lenz's law, the direction of this current opposes the cause for which it produced. So when the flux is increased in the shading portion, so it is opposing the cause, and hence the flux is increased. And initially the greater portion of the flux passes through the unshaded side of each pole, and the resultant lies on the unshaded side. When the flux reaches its maximum value, the rate of change is 0. Now there is no change in the flux, and the EMF and current in the shading coil becomes 0. So flux has to reach the maximum value in the operating condition. There will be no EMF and current in the shading coil. It will become 0. And flux is uniformly distributed over the pole faces, and the resulting field lies in the center of the pole. So when we talk about which direction the resultant field is there, so it will be in the center of the poles. So after this, as the main flux tend to decrease, now the flux will decrease because flux is alternating in nature. The EMF and current induced in the shading coil now tend to increase the flux. So because the flux is alternating in nature, so when the flux will be decreasing, the current will increase the flux on the shading pole side, and the resultant lies on the shading portion. So a revolving field is then set up, rotating from unshaded portion to the shaded portion, creating a starting torque in the rotor, causing it start the rotating. So in shaded pole induction motor, the advantage is, so when the flux will decrease, the current will increase the flux, and when the flux will increase, then the current will decrease the flux. So you will be having a constant torque operation. So here, due to the shading band, you will be having the relative change in the current and the relative change in the torque produced. Here you have very small torque, which is about 50% of the full load torque, and the efficiency is also low due to continuous power loss in the shading coil. So shading coil will have some power loss, so efficiency will be less. Generally used in small fans, electric clocks or gramophones. And the direction of rotation depend on the position of the shading coil from unshaded to shaded portion. So where is the position of the shading coils? So that will decide the direction of the rotation. Direction of rotation cannot be reversed unless the position of the pole is reversed. So unless and until you change the position of the poles, you cannot reverse the direction of the rotation of the field. So we have seen in this lecture the different types of single phase induction motors, and the idea is that single phase induction motor is not self-starting. We have to start it, and hence we require certain phase angle between the starting current and main winding, which is produced because of different capacitors and the shading pole as well as the split phase. So this overviews the classification of single phase induction motor, and next lecture will focus on equivalent circuit of single phase induction motor. Then we will solve some problems in the tutorials. Thank you for now.